Chapter 7, we're getting into a whole new thing now. And we're back to atomic structure. Can you still see the board? Is it still visible with the light off? Okay, all right, because I will still be writing a little bit on the board. Okay, let me just take you back a little bit to chapter 2, okay, and just review things which I know you know. Okay, there's no way that you cannot know this. So you remember the structure of the atom, right? Where the nucleus was in the middle and the electrons are outside, right? And in the nucleus you have neutrons and protons, right? And you also know that protons and electrons are same numbers. So far? Okay. So this much we know, okay, already about the atom. That atomic model is what we call the nuclear model, okay, of an atom, because it just talks about the nucleus, okay, of the atom in there. So it's called the nuclear model of an atom. Now we're going into what's called the quantum model, okay, of an atom. And the quantum model of an atom came around only when certain discoveries were made. Until those discoveries were made, one couldn't really come up with this model. Okay, so, and this model also came about not only because of the discovery of certain things, okay, but also because people were curious as to where the electrons are. As far as we are concerned, at the time of the nuclear model, is that the nucleus is in the middle and the electrons are out here, right? That is what Rutherford established, okay, back in chapter 2, the gold foil experiment, is that you have all the positive in the middle. So, but then the question becomes is, where are these electrons? Where are they located? Okay, and so I gave you an example back then as in that the size differences between the nucleus and the atom and the whole atom is like if you had a huge football field, not a huge football field, you had a football field and a football. So the football is in the middle and that is the nucleus, okay, which means you have all of this empty space, okay, in there. So where are the electrons, okay, in that empty space? That's really what we're talking about in chapter 7, okay, and chapter 8 also a little bit. So that comes to the what we call the quantum model, okay. So this establishes the location of electrons, and this is a little bit of a development, okay. It's not something that I can tell you right away, okay, just like that, and be over with, okay. It's just a little bit of a conceptual development. Electromagnetic spectrum is something that you should all know, okay, and again, not this week, after the exam, okay, then you will start memorizing the electromagnetic spectrum, which really is not that hard. By the time I get done telling you about it, you will remember a whole bunch of things, okay. Electromagnetic spectrum is something that you get from the sun, okay. When the radiation is coming from the sun, it's actually called the cosmic radiation, okay. That's what you find in the universe. As soon as the cosmic radiation hits the Earth's atmosphere, it kind of breaks apart into different wavelengths, just like you would see a rainbow, okay, through a prism or anything. So once you see a rainbow, you know how things are separating into different wavelengths and frequencies. It's the same thing with cosmic radiation. So when it hits the atmosphere, it breaks apart into all of these different categories of radiation, radio waves, microwaves, infrared, and all of this, okay? So, but before I get too much into this, I need to go over a little bit about wavelengths, okay, with you. So let me talk about waves. And this is a little bit more physics than chemistry, okay? However, we still need to talk about this. So we all know that there are waves in this world, okay, and sound travels in wave, light travels in wave form. So just a little things, you know, a few things about the wave. Okay, let me turn on the light, make it easier. So here, if you have a wave, there are a few features about the wave that you should understand. Okay, one is that a crest going whole up and then all negative. Okay, in the graphic scale, this is called the wavelength. And the wavelength is represented by this symbol, okay, which is called the, anyone? Lambda. Greek symbol lambda. Okay, and so That's called wavelength, okay? One full crest going up, and then one full crest going down. In America, they teach it a little bit different. That's how they teach it everywhere else. But in America, it's slightly different. In America, they teach from crest to crest, okay, from the top to the top. But the way I learned it, it's one full cycle starting from 0, going all the way up, and then going all the way down. Okay, that is your one full wavelength. Okay, and wavelength is a length, so the units will be, yes? What are the units for length? What happened? Suddenly, yeah, meters. Okay, so it would be in meters, or it would be in nanometers, okay, or something like, yes, nothing so weird. Okay, all right. So that's called wavelength, okay, which is the length of one wave. Okay, then I'm going to draw two wavelengths here for you. And let's say this scale from here to here and here to here is 1 second time scale. Okay, 1 second time scale. So in 1 second time scale, here is the wave that is passing, and here in 1 second time scale, this is the wave that is passing. Okay, so do you have more waves over here or here? Top or bottom? In the bottom one. Okay, and that, how many waves are passing through in 1 second, is called frequency. Okay, very good. So frequency then is lambda per second. Okay, how many wavelengths you have passing through in 1 second. Okay, so looking at these two things over here, where you have a wavelength here and a wavelength down here at the bottom, if the wavelength is long, your frequency is small or large? Small. And when your wavelength is small, the frequency is higher, okay, which means that the relationship is inverse, okay, between them. All right, frequency is lambda per second, and you also know the frequency unit as hertz. Okay, yeah, that's something you've heard before. So frequency is represented by a symbol called nu. It's like a V. Okay, again, this is a Greek letter. Okay, it's called nu. So that's frequency and lambda, okay? Two new symbols here for you. And the relationship between lambda and frequency is that of inverse relationship. So that's what this is, okay? So those are the two features of any wave. The third feature of any wave is the height of the crest, okay? And the height of the crest is called amplitude. This is the only thing we are not going to touch here. This is something that you do more in physics, okay, and not so much over here. Amplitude. If you change the amplitude of a wave, does that change the frequency?
Yes.
No, it does not change the frequency. Does that change the wavelength?
Yeah.
It does not change either of those two things, okay? Changing the amplitude is turning the volume up on your song. That's amplitude, okay? So amplitude will just amplify everything. That's all it is, okay? So it doesn't change the frequency, doesn't change the wavelength, okay? And you might have heard, and you may have heard this on my pencast, if you make me go faster or slower, okay, that is the change in wavelength, okay, that you're doing. But if you increase the sound, if you crank up the volume, that is just amplitude, okay? So those are the differences between all of these three things, okay, over here. And that is what is shown in this slide also, okay? Here you have the wavelength, which is lambda, frequency, how many wavelengths are going through over 1 second of time, and the amplitude, which is the height of the wave. The amplitude doesn't have much to do with chemistry so far, okay, because it's just a volume thing. And then right here, this relationship. So let me come back to that one then, is if you have a proportionality, the only way you remove a proportionality is by adding a constant, okay, to that. So the constant that is added here is C, and so C is actually the speed of light. And so, my God, I have no room anymore. This takes up all the room. So then lambda nu is equal to c. Okay, so which means if you multiply the frequency with the wavelength, you should have a constant, and that constant is the speed of light, and speed of light is 3.0 times 10 to the power of 8 meters per second. Okay, and when you get to physics, you will never forget that number. Okay, just like we have our Avogadro's number, they have the speed of light. Okay, and so you won't forget that number there. Okay, so this is the properties of wavelength, which is really what is given to you over here in this slide. Okay, all of these relationships. I usually don't give you much calculations to do, because when you get to physics, you will have enough calculations, okay, on wavelengths and all of that. So I don't give you much. There's just a little bit. There are some examples in here, but otherwise I don't do a whole lot. Okay, so let's go back to our wonderful electromagnetic spectrum. Okay, so now let me tell you what this is all about. So I know it's not very clear, probably from the back there, or maybe actually it might be clear. And this is page 272 in your textbooks, okay, if you want to look. It's a little bit different. I like this slide a little bit better because it's pictorial. Who doesn't love pictures? We all do. Okay, and so right here, no, it's not very clear, even from here, okay. But the wavelength is going from here. This is 10 to the negative, I think 3 or 5, okay, to the 10 to the power of 13. 10 to the power of 13, and this is in nanometers. Okay, nanometers is negative 9. Okay, negative 9. So if you were to go to meters, that would be 10 to the power of 4 meters actually. Okay, so that's a really long wavelength, okay, that you're talking about. So this is a long wavelength, so the frequency here must be very short, right? Remember inverse relationship. So this is a short wavelength, so the frequency must be very high over here. That's how this electromagnetic spectrum is, and that's how you understand electromagnetic spectrum. So the wavelength increases as you go there, and the frequency increases as you go towards the left side, okay? You can also turn the electromagnetic spectrum around, but I like it this way, keeping my radio on the right-hand side and my X-rays on the left-hand side. It's just easier to remember, okay? If you turn it around too much, then you keep confusing. Okay, so best to learn it only one way and not change it too much. Okay, so which means the most harmless of all the radiation is the radio waves. Okay, and nobody has died yet of listening to a radio. Okay, not yet. Those frequencies will not hurt you, okay, at all. So that's what radio waves are. And radio waves were also the first ones to be discovered. Anyone knows who invented the first radio? Yeah, when I'll be 50, then I'll have more time. Right now, I have no time to figure this out.
Was it Edison?
What is Edison? No,
Was it
not
Edison?
Edison. Yeah, I know what you mean. Yeah. Marconi. Marconi was the first one who actually invented the radio. And he's also the first one to actually use the radio for the first time. Okay, as well, the radio waves for the first time. Now we can transmit anywhere, any place. Okay, no problems at all. Okay, we have such good connections now, the towers, and they carry all the waves. That's not a problem. But previously, none of these things were known. Nobody knew how to actually use these frequencies. So anyhow, Marconi was the first one to use the radio waves, and they used the radio waves actually to catch a killer. That was the first time they used the radio waves for intercontinental work. Okay, and so there was a lady, call her a woman maybe. She was, what do they call them? Black widows, right? If you've killed all your husbands, right? 3 or 4 of them. So she was escaping from England and she was coming to America at that time. So that's when they actually radioed it, okay, that she's coming. So they caught her, sent her back. Okay, that was the first time the radio was actually used to solve crime also, and also the first time it was used intercontinentally. So it was quite a big deal, you know, at that time. So anyhow, that's radio waves. Coming on to microwaves, which is the next thing, and microwaves are a little bit stronger or higher energy than radio waves because they have higher frequency. As you're going over here to this side, towards gamma rays, okay, and we all know that. I mean, it's not such a huge question. Is gamma rays are the most dangerous one, right? We know that too. And X-rays are very dangerous. So we'll talk about that also as to why they're dangerous. But they have high energy, okay, in them. So we'll talk about that in a minute. But in any case, radio waves and then microwaves are over here. And by the way, these wavelengths And these categories that are made, as in radio waves and microwaves, these are all, of course, man-made. Okay, so we decide that from this region to this region, we're going to call radio waves. This region to this region, we'll call microwaves, and so on and so forth. Okay, so if you see something different in a different table, that's because they've just, either added something else in there to make it better or something else. Okay, but otherwise, these are all man-made categories. Okay, over here. So microwave is a little bit higher in energy than radio waves, because now you know that you can use microwaves to heat your food, right? You can try that on a radio, it's not going to work. Okay, you cannot heat your food using radio waves. So how does that work? Anyone know how microwaves work? I know how to press the buttons. Yes. Anything? Kevin?
It works off the electromagnetic waves, right?
Yes, but
It
what
starts
is it
shaking
heating?
the hydrogen atoms.
In
It shakes the water molecules.
water molecules, right, yeah. So I think we've talked about this, yeah. So water molecules are the ones that are actually being moved, okay, in there. So if your food does not have water in it, it will take a longer time, okay, to heat. And that's why they always like you to put some water in there, okay? That makes it better. And also if your food has water that's sitting on one side and not on the other side, and kind of moved, shifted, then you know there is some uneven heating going on in the food. Some parts of it will be still cold, while some part of it's going to be really hot. Okay, and so that happens also. But in any case, that's a microwave for you. Okay. You also know that there are all these myths that are going around that microwaves will kill you, right? Yes, Malik has heard about that. So. Yeah, so there are two myths around. Eating microwave food will kill you, and then there's also about that if you get too close to a microwave, the radiation will kill you. Well, first of all, get a life. Don't stand next to the microwave, okay? So if your food is heating up, go away from there, okay? Don't stand next to it. And the second thing about the food being radiated in there, okay? So here's where your scientific knowledge becomes really important, because you as a scientist can then decide, okay, is microwave, Marcel, is a microwave that high in energy that it's going to change your food, okay, so much that you just can't eat it anymore, okay? Or is it just heating the water molecules, as we were saying?
It's the same concept with heating metals to orange. You heat it so hot that you shake the atoms to orange.
Right, so that's why we don't put the metals in there, right? And
Right.
so the metals will give off sparks because they actually start ejecting electrons, okay, from there. So that's why you get a sparks. The other thing you should never heat in a microwave is what?
Metal.
I didn't hear anything.
Should never use metal in a microwave.
Metal, yes, we've heard, but
AIDS.
Styrofoam.
What's that?
plastics, yeah, plastics, some plastics are not good. Okay, yeah, if you keep them from 10 minutes or so, then yeah, some of those plastics will come out really weird looking, right? So you don't want plastics in there either. But we tend to eat in plastics, right? So much. What to do? You know what? Just kill me. I don't care. Okay. But in any case, the other one is you should not keep a raw egg in there, right? Have you ever tried that? No, don't try that. It's going to be really bad. Okay, just explode. And that's because the water molecules are trying to come out, right? That's the whole theory behind popcorn. Okay, is that you have water in there, and the water tries to come out as steam, and then it pops the popcorn. Okay, and so that's kind of the same thing with the eggs also. Don't try it. Okay, nobody's going to be happy cleaning that one up. But the metals definitely you should not put in there, because the metals will give off electrons, and then those will give off spark, and that can actually ignite something. Okay, so that's a fire hazard. Okay, so I will leave it to your bright minds to decide whether microwaves can kill you or not. Okay, and so you as an educated person, as a scientist, can study and then decide for yourself, okay, whether that's good or not. Okay, the next thing comes here is infrared, and infrared is something that you can feel. Microwaves you don't feel, right, because we're never close to that, and thank God we're not inside a microwave either, okay, but infrared you can feel. So if you go out in the sun, you can feel the heat, okay, on yourself, and that's, a lot of it is infrared radiation, okay, in there, so you feel the heat from there. The other application of infrared is primarily it's for heating, okay, without causing much damage, okay, to anything. So it's a very mild kind of a heating going on. Infrared is also used for night vision, okay, because we all emit some sort of a heat energy, and that heat energy is infrared. And so night vision goggles and all that, those actually all work on this frequency, okay, over here. And then we have the visible region, which is so tiny, and yet it is so powerful. Look at us, we're also colorful, okay? And so that's the little tiny region, that's the visible region, okay? And that's also, you know, what gives you the rainbows right here. So, but it's a very small region, and again, nobody has ever died from wearing a pink color or a red color, okay? So which means that until now, we're pretty safe, right? Nothing has happened to us. Nothing has really killed us, okay, yet. Oh, by the way, radio waves can kill you, right? You might have heard about the cell phones and brain cancer. Yeah? Okay, all right, I'll leave that to your educated mind too, okay? So you can decide what happens with that. Okay, after visible is the ultraviolet region. Ultraviolet region now is the bad one, okay? Because now we're getting into higher energy, and in Florida, of course, it makes such a big difference because we are really exposed a lot to radiation over here. So you usually should not go out on the beach, or if you're going to be out in the sun for too long, you have to use sunscreen, okay? And so to protect yourself. So even somebody like me with a little bit dark skin who has a little bit natural protection, but still, okay, if you're exposed too long, you will still get exposed to ultraviolet, which now is so high in energy that it can cause mutations in your cells, and that can cause skin cancer. Okay, so one has to be really careful when going out in the sun and staying out too long. So that's ultraviolet radiation. All of this, okay, then coming to X-rays and gamma rays, all of this we are protected a little bit by the ozone layer. Okay, so Earth has the atmosphere, and then it has the stratosphere. So on top of that is, of course, the ozone layer. Okay, and so when the radiation hits the ozone layer, a lot of the radiation is actually absorbed by the ozone layer, which is why we love our ozone layer. Okay, why we want it to be there. And then the rest of it will filter through. Okay, so we are protected very much by the ozone. If the ozone layer goes, then we will cook, okay, on Earth. So it's a good thing that it is there. So then we get to X-rays, and X-rays are getting to be very high energy because X-rays will pass through your body, okay, and you can actually see inside the body then. And so X-rays are getting to be very high energy. X-rays, even the nurse will leave you alone in the room. She will not stay, okay, and the only thing that will stop an X-ray from passing through are lead, something that's very heavy, okay, like a heavy metal, or concrete, okay, that will stop the radiation from passing through, okay. All the rest of it is, it's fine, it's passing through, no problems, but X-ray you can stop by using concrete or something like that. And then we come to gamma rays. Gamma radiation is the highest energy over here. After that we get to cosmic, by the way. So gamma radiation is the highest form of energy. Gamma is also the hardest to form. You will not experience gamma radiation if you go out. You won't even experience X-rays, by the way, okay, when you go out, because those are all filtered off by the ozone layer, okay? But the X-rays you experience only in doctor's offices and all of that, okay? And then gamma radiation is the same way. Gamma is even more protected because you get gamma radiation only from radioactivity, okay, and nothing else. So natural radioactivity or artificial. So wherever you have radioactivity, that's where you can find gamma radiation. So for places like hospitals and some of the national labs that we have in US, those are the places that you can find gamma radiation, okay? So it's you really have to get approval from the government before you can actually generate gamma radiation. So it's something that the government really monitors because you need radioactive material for that, okay? And so that is a highly monitored kind of chemicals there. But gamma radiation is very dangerous. It causes cancer in no time. It forms like a chemical burn, so you feel like you're burning and all that, but then it causes more than that, okay? It causes mutations also, not just a burn. So it's very dangerous. Again, you can stop that by concrete and all of that. So when there was a whole thing about the fallout of nuclear war and whatnot, people made bunkers, right? And they stayed in the bunkers and all that. So the bunkers were all made of concrete, thick concrete walls, so you can protect yourself from all of these radiations, okay? So this is the electromagnetic spectrum, and please, you'll have to know this, okay? You'll have to know which is the low energy, which is the high energy, okay, for yourself. But that's what it is. Do you have any questions about this before I move on? Was I speaking too fast? It's perfect. All right then, let's go on. So this is the wave nature. And here's one problem. Just using simple equation that I wrote up there also. Okay, it's the same one. So you can go through that when you get time. And then the nature of light. This is where the fun begins. Okay, and a lot of discoveries were made earlier in the 20th century, later 19th century. So between like 1890s until about 1940s and 50s until the World War II, until the end of World War II, a lot of discoveries were made. Those 50, 60 years were just too much. Okay, there was just so much going on at that time. And that's where light was actually studied as well. Okay, and one of the things that's really hard to study about light or anything that you can't see is that because you can't see it, you just don't know how to study it. Okay, and so all of this you're going to learn in physics, okay, which is how you know if something is traveling in waves. So we know now that light travels in waves, but how do you know that? We know that sound travels in waves, but how do you know that? Okay, that sound travels in waves. So to know all of those things, you have to set up certain experiments, and this is called a diffraction experiment. And if you ever get time when you're older, or even now, there are some nice documentaries where you can actually hear about how all of these things were discovered, that light actually had a wave property, okay, in there. So you can study how the diffraction patterns work, and that's how they figured out the wavelengths of all of these different radiations also, initially. And then the most important discovery was the photoelectric effect, okay, which is what led to a lot of things that happened. And photoelectric effect, I'm not going to go too much into it. Again, you will learn that a lot more in physics. What it is that if you take a radiation, something like a red light or a blue light, any kind of radiation from the electromagnetic spectrum, and you hit that to a metal, okay, any kind of a metal piece, copper, iron, whatever it is, then according to the energy that is given to that metal with that radiation, electrons will be ejected from there. Okay, that is photoelectric effect. And Einstein studied that a lot. Okay, so it was first observed by Hertz, but then Einstein picked it up and he studied the photoelectric effect a lot, because then he was trying to figure out that is that if you increase the intensity of that red light, could you get more electrons out? And he could not get more electrons out. Okay, so which means that whatever the red light energy could give, that is it. Okay, as far as photoelectric effect was concerned. So he could not tell. He said, you know, if there is more intensity, then you should have more electrons coming out. Okay, but that did not happen. And so Einstein was kind of stumped. And at that point, there was a scientist by the name of Max Planck. Okay, and I don't know if you've heard of him. Nod, shake. Yes, no, okay. Max Planck, great scientist, great physicist. Okay, and he's the one who then discovered this whole thing that we now call quantum chemistry, quantum physics, okay, and all of that. And then he was the one who discovered that, and then Einstein piggybacked on him to then explain photoelectric effect even more. So let me come back to our wonderful wavelength. Okay, over here, light, and Max Planck said that if you have, like the electromagnetic spectrum that we were talking about, if you have something like microwave, and then if you have something like the ultraviolet radiation, and you have more energy in the ultraviolet, how does it have more energy in there? Okay, and then he tried to relate that to frequency, okay, which we just talked about. So he said, okay, so there is a wave that is going at a regular wavelength like this, and then there is a wave that is going at a higher frequency. Okay, this one is providing higher energy. So how is it that it has higher energy than the other one? Okay, which means that the wave is actually carrying the energy on it. Okay, so then the question is, how is the wave carrying the energy? Okay, on a wave, right? And to this, I want you to imagine, it's so nice to imagine sitting on the beach. Okay, and if you sit on the beach, you would remember seeing waves coming to you. Yes? Nod? Okay. You've seen waves coming to you. Now imagine there is no water. Will you see any waves? No. And that's what he was talking about. Okay, is that if you remove any of the waves, then it has no energy. Which makes sense, right? If you don't have any waves, you don't have any energy. Which means that those two things are related very closely, okay, to each other. You have to have both in order to have this property that we're trying to explain. So what he said is that the light energy that we have, the energy that we're talking about, travels on the waves, okay? And they travel in form of little packets of energy, which are called quanta, okay? So that's how the word quanta came about. And so quanta is the little packet of energy, okay, that travels on the waves. So how does it go? And again, you know, this is just hypothetical, but here, if you think of it as a little packet of energy, this is all it is, okay? And so if you have packets of energy on a wavelength, or on a wave, which is like this, then obviously if you have higher frequency, then you're getting more quanta of that energy. If you have a lower frequency, then you have lower energy coming through, okay? And this is what started what we call the dual nature of light, okay? And the dual nature of light is one, that it travels as a wave, and second, that it travels as energy, okay, like this. So the energy that is coming from the sun is actually traveling in wave form. That's essentially what it is, okay? So that is called quanta. Einstein liked to call it photons, so you might hear photons, which is the same thing as quanta is, okay? I like quanta, it sounds cool, and this is what Max Planck said, okay? And so, but both of these things actually mean the same thing, okay? And so then he related the energy to frequency, which he said that the higher energy, the higher the frequency, or the higher the frequency, the higher the energy. So which means that there is a direct relationship between the two, okay, between energy and frequency. And so now he can say, okay, to remove that, you need a constant, and guess what? We get a Planck's constant because it was Planck who discovered that. Okay, so then that constant there, h, is Planck's constant. Okay, so E becomes h nu. Okay, and so that is how you calculate how much energy is being coming from one sort of wavelength or the other. Okay, so now let me go on to the next slide. Which is what this is. Okay, so here we have a lot of quantum little packets of energy that's going through, and here is the what we call Planck's equation then. Okay, it's a very small thing. It's E is equal to h nu. You cannot forget that part. Although we don't use it so much here. Okay, when you get to physics, you use it a lot more. In this chapter, we use it just a little bit. Okay, but otherwise we don't. So E is energy in joules. H is Planck's constant, and this is the value of the constant. 10 to the negative 34, that's a very small number, okay, 10 to the negative 34, very small number. The S here stands for per second, and if you remember, the units of frequency was wavelength per second, okay, so that's the per second, and then of course nu is the frequency here, okay, so that is the quantum theory that was, that came from Max Planck, okay, and so are we good with this? Yes? Okay. Because once this happened, then we can explain photoelectric effect. Because if now Einstein was trying to radiate something with red energy, then you only have a certain amount of photons coming through. Okay, the only way you can change the number of electrons that come from any amount of energy is by changing that energy. So going from red to blue will change the amount of photons, okay, hitting, and that will change the number of electrons. But if you just amplify the red energy, that doesn't do much, okay, for anything. And once you get to physics, it will get really, really interesting, because all of this discoveries, they just led to so many things, okay. The very fact that we have lasers now comes from this also, okay, and so it's all quite interesting. One other practical application of photoelectric effect and all of that is also in the elevators. When you walk into the lift, you see how when the door is closing and you want to walk in and suddenly opens up again, right? And you think, oh, it opened for me, right? Yeah, but there has to be some mechanism on how it opened up for you, okay, and that is a motion sensor, which you just think of as a motion sensor. But what is a motion sensor? Okay, a motion sensor has to be something that you kind of interrupt somehow, okay? And so what a motion sensor is kind of like photoelectric effect, where you have a source, okay, and where you have a receiver. So in the elevator, that's how it works, is you have a source and you have a receiver, and there is electron stream going through it. And so if you block that electron stream, you open the door again, okay? So that's kind of how some of these things work. And things change as we get, new technology, things will change also. But in any case, that's how we can think about photoelectric effect, okay, to help us out. Okay, so then here is a solved problem for the E is equal to h nu. So calculate the energy in joules. So you can do that for any wavelength. Okay, you can do that. So first you change the wavelengths to frequency using this equation, and once you do that, then you can go ahead and plug it into Planck's equation and figure out how much energy is given. Okay, so nice little calculation. It's really not that much. Okay. So far we haven't even talked about the electron, right? We're still learning about all of this light stuff, okay, going on over here, because all of this is the foundation for where we are going now, okay? And the next scientist, okay, who comes into play is Niels Bohr. And Niels Bohr is the one who wanted to know where these electrons are. Okay, so he thought, okay, let me try this out and take any element and bombard it with energy and see what happens. Okay, what do I get? Okay, so he did that. Okay, he bombarded an element, and he started with hydrogen. Everybody starts with hydrogen. J.J. Thomson also started with hydrogen. Okay, and so what he did is he provided a certain wavelength. Okay, over here, there's a slit just to make sure that you're getting only one sort of radiation coming out of there. Here is the element. So this is a prism, just to show you that a prism can, separate out the wavelengths. But he had an element over here. And so what happened is that that element gave off radiation then at a very specific wavelength. Okay? This spectra is called a line spectra. There are two kinds of spectra possible, a line spectra and a continuous spectra. What you're sitting under right now is a continuous spectra because light is just diffused all over, okay? So there's no particular segments, okay, to it. But in a line spectra, you get very specific radiation at very specific wavelengths, and there's nothing in the middle, okay? And this, of course, is the colors which shows you that the radiation is coming out in the visible region, okay? That's where it's coming out. So that kind of boggled him a little bit as to why this is happening, because what he was expecting was a continuous spectrum, not a line spectrum like this. When you have something coming out a very specific wavelength, it means that something is very organized, okay, in there. So the whole organized thing, how can that be, okay? And remember what he's trying to study. He's trying to study the atom. So what he's trying to figure out is that if you have an atom, and here are the electrons, where are these electrons located? That's what he's trying to figure out. So when he gave energy to the atom, and then you're getting a line spectrum, how does that work, okay? There are two kinds of spectrum. One, of course, was the continuous and the line. The other kind of spectrum is one is emission, one is absorption spectrum. So a line spectrum is actually considered a fingerprint of an element, okay? So which means that no two elements are going to have the same line spectrum, okay? So which makes them very unique, and this is how we actually discover new elements or elements in the space also, okay? So if you are thinking, how do we know that on Saturn that there is carbon or methane or anything like that? Well, this is how they do it, okay? Because everything is going to have its own line spectra. So what he said, what Bohr said, is that an atom has several shells, okay, in an atom, okay? And so once there are several shells in there, the electrons are in a particular shell. So when you give them energy, which means when they absorb the energy, that takes them to the next level or to the next level. they cannot go in the middle over here. So which means that there is no electron in the middle space here, there is no electron in the middle space here. They only go from one shell to the other shell. Okay, these shells are called N. So this is N is equal to 1, N is equal to 2, N is equal to 3. You can have 4, 5, 6, 7, okay, as many. And then the emission spectra, which is when energy is given off, is when these electrons over here then, when they're excited and you take off the energy, then they have to go back to their original position. Okay, so there is a ground state and then there is an excited state. Excited state comes from giving them energy. Okay, so which means again, you have electrons going back to a specific location, nothing in the middle anywhere. Okay, and that's how you get the light spectrum. Because there is a specific amount of energy given here, there is a specific amount of energy given over here. Okay, so that's what we call a light spectrum. Almost equivalent to the fact of what we have in this classroom. Okay, when you come in here, you come and sit near a specific place. Okay, nobody sits here in the middle. Okay, anywhere in this pathway. All right, and that's what's a major no-no. Okay, nobody sits here. Here's an allowed space. Here's an allowed space. So that's what these are. These are allowed spaces. Okay. Now you can change your entire look of the atom now. Okay. Until now you were looking at it as a nuclear model. Okay. Nucleus in the middle, electrons outside. Now I want you to think of the atom as a planetary model. Okay. So where you have the sun in the middle and you have all the planets around, right? And the first planet is Mercury. Okay. And then we have Venus, and then there is Earth, right? Okay. So is Earth going around on a particular rope, or is there a road? Is there a road? Is there a highway? No, it's going around just because of the gravitational forces, right? Okay, so there is a specific path for the Earth. That's where it goes. That's it. It knows it, right? Itself. If you move the Earth away from that gravitational pathway, do you think we will survive? No. Probably not. It's the same thing here. Okay? So the electrons are moving around in a very specific pathway. Okay? They're not going anywhere else. That's how I would like you to look at the atom now. Okay? As a planetary model that will help you understand. Yes, George.
For the line spectra, use the example of methane on Mars. So you could blast energy into compounds as well and tell what elements are in the compound?
Yes,
Okay.
you can do that. Yes, we have instruments. Instrument makes things easier. Yeah. Okay, so that's the line spectrum, and these are different ways of calculating how much energy is required at different n numbers. Okay, and then so here are the different things called the ground state and the excited state right here, and then you can calculate the amount of energy from N1 to N2. So going from one shell to the other shell, you can calculate how much energy is required for that. Okay, so which means that those line spectra are actually not a mystery. Okay, you can calculate everything. Okay, once you know which shells you're talking about, then you can calculate how much energy is required to electron to jump from one to the other. Okay, and all of these are called the different kinds of line spectra, and there's a Paschen series, there's a Balmer series, and there's a Lyman series. What we look at most time is the Balmer series, okay, because that is in the visible region, so it's much easier and much more fun to look at. So all of this is the line spectra for hydrogen. This would be the Balmer series, okay, but otherwise you can look at transitions. In the Lyman series, you look at higher transitions, okay, where you have n is equal to 1, going all the way to n is equal to 5, okay, or 6. And so all these different transitions you can study. We will not do so much, okay? I just need you to know that these things are possible, but when you get really more into quantum chemistry, then you do a lot more, okay, of all of these calculations. So what we will do next time is we will talk about those shell numbers, okay, and how to figure out how many electrons you have in there. That will be next week though.